So we don't have a lot of time, so let me be fast on this thing that I want, the final thing that I want to tell you about the chain branching. We had gotten to a point where we found essentially the first term, okay, in a power series here of so the so-called slow invariant manifold, which we call M epsilon, okay? Now, just out of curiosity, how do you find the other terms, H1 and H2, which actually make the manifold invariant? Okay, meaning that if you start from a point, you will integrate the system and stay on that manifold. Well, I've already told you some time ago, you have to enforce essentially invariance. Okay, so remember that the system we had written was a system in the form dx by dt equals g of s, so the right hand side of the slow term. Okay, so x and y. So this is the slow evolution, and then we had epsilon dy by dt. Okay, and gf standing for fast. Okay, so we have the fast, slow, so singularly perturbed form. Remember now that we have to substitute the fact that y now is constrained on the manifold. So y is equal to h of epsilon x. Okay, so if we substitute this position here in this equation, for example, we have that we have epsilon and dy by dt. We can write it as essentially dh epsilon by dx and dx by dt. Okay, and this will be equal to, again, the right hand side as a function of x, and then y, well, we have to substitute for y the slow manifold. Okay. Well, not only this, but then clearly if we rewrite it, dx by dt, we know exactly what it is gs. Okay, again, of a function of x and h epsilon of x, okay, is equal to g of f x of h epsilon. So this is it's a condition on h epsilon, if you will, which enforces the fact that it has to be invariant. So it has to be one of the solutions of the system, essentially. Now, clearly, we know what h epsilon looks like. Okay, so for example, dh epsilon by dx, okay, is we can call it h0 prime of x plus h plus epsilon h1 prime of x, and so on. Okay, we know that we know the form of the right-hand sides. Okay, if you remember, for the chain branching system, gs was minus x minus xy, and g of f was x plus alpha minus 1, x epsilon, xy, sorry, minus gamma y. Okay? So we can substitute now for y, okay, here, here, and here. We can substitute h epsilon. So I'll be fast here because it's a long procedure. So gs will be minus x times y, but y is equal to h epsilon, okay, which is again h0 plus epsilon h1 plus epsilon h2, epsilon squared h2, and so on. Okay, and the same thing we do for gf. Okay, x plus alpha minus 1, x times, I'll just write this brackets here just to remind ourselves that we have to substitute the series in here. Okay, minus gamma, and again, the series, okay? And so what we do here, we substitute everything in the invariance equation, okay? And we get a very long and very boring expression, okay? So epsilon h prime 0 plus epsilon h prime 1, etc. Okay, gs is this thing here, minus x of this, and so on, okay? I'll equals gf, which is, again, minus 1x minus gamma, okay, of the series. Now, how do I find h1? So what we do is we compare equal orders of epsilon, okay? So what does it mean? Here you have a left-hand side, okay? And on the right-hand, and you have a right-hand side, okay? So what you do is you expand both the left-hand side and the right-hand side, okay, in powers of epsilon, starting from order 0, then order 1, order 2, order 3, and you essentially equate all the orders, okay? And by equating all the orders, you will find, essentially, sequentially, you will find first h0, okay? Then you will need the derivative of h0, which you have, because you have h0, and you'll find h1, okay? Then you'll need the derivative of h0, h1, etc., and you'll find h2, okay? And find h0, h1, h2, and so on, okay? So it's a long story made very, very short, okay? It's one of the classical techniques of like perturbative analysis or asymptotic analysis, okay? But really, we don't really need H epsilon, okay? It's the only advantage is that it's invariant, but really, we don't really need it, okay? This is just out of curiosity, how do we find, what's the big procedure to find all the terms in the expansion? I mean, as long as you find the first term H0, you'll know most of the things that are needed. But anyway, what is important is that we finished analyzing the first of the two toy models, okay? The first one is, again, the chain branching model, which has shown us that a certain kinetic mechanism comprising an initiation, a termination step, and an intermediate step, which is a chain branching step, can be explosive. Can be explosive means that it can generate a very large, in a very short time, a very large number of intermediate species, okay? That's one characteristic. The other characteristic is the so-called, so the other toy model that we're going to talk about now is the so-called thermal explosion. Okay, or better known as the Semenov or Semenov's system or model, if you will. It's the same thing, okay? If you've noticed, we haven't, in the chain branching, you can hear me, right? Please tell me yes.
Yes, yeah.
Okay. In the chain branching, we have never talked about temperature, if you've noticed, right? We consider the temperature constant, which is obviously not very realistic, okay? always remember that to keep the temperature constant in a system that has a number of endothermic or exothermic reactions, you need to subtract or add heat, okay? Now, the thermal explosion covers essentially the other half or the other aspect, okay, of kinetic systems, or combustion kinetic systems, which is the fact that the rate of reaction is also dramatically, okay, dependent on temperature. In fact, it's exponentially dependent on temperature, okay? So you can have explosions, not just through a proliferation of radicals, that what we've seen in chain branching, but also as a result of an uncontrolled increase in temperature. So what you have to think about in terms of Semenov's system is a closed vessel, okay, of a certain volume V. In this vessel, we're going to add a combustible mixture, okay? I mean, a gaseous mixture of some kind, comprising an oxidizer and a fuel, okay? And then we're going to surround, essentially, this vessel, which we keep, okay, with a cooling system, okay? So the walls of this vessel, we're going to keep at constant temperature T0, okay? So essentially, we're going to have two phenomena here: a production of heat, which we can indicate with a heat flux here, Q dot plus, owing to the essentially an exothermic reaction inside, okay? And then a cooling system or a cooling jacket, okay, which subtracts some of the amount, okay, of heat. So we have heat addition inside the vessel, and then we're trying to get some of it, if not all, out, okay, by cooling jacket. Essentially, it's a convective system, okay? You can think of it as, for example, tubes of where you circulate some water, for example, okay? So by convection, you're actually extracting some heat out of the system, okay? So that's more or less the structure of the Semenov's model. As you can see, and as you will see, we're not going to concentrate too much on the kinetics. In fact, the kinetic can be as simple as possible. You have a reactant, okay, which essentially produces products, okay, through a process, a kinetic process of rate of reaction constant K, okay? So it's a one-step, irreversible kinetic mechanism. Very, very simple kinetic reaction. And of course, I will add here, it's an exothermic, okay, process, okay? So we want to understand under what conditions, okay, we have, or we will have an uncontrolled, okay, the temperature will indicate as T, we will have an uncontrolled increase in temperature here, okay? So in some sense, you have the competition of two phenomena, okay, which depend on temperature in a completely different way, okay? You have the exothermic chemical kinetic process, whereby you have an increase in temperature, but remember that this process, as we will see, will be essentially evolving at a rate which is a very non-linear function of temperature. In fact, it's an exponential. And then the subtraction of heat, which will go, as we will see, linearly with temperature. Okay, so let's start. We we'll call, with the variable C, the molar concentration of the reactant, okay? And so how do you write the rate of change of the molar concentration of the reactant? Well, it's pretty straightforward. Look at this reaction. So we have minus C, okay? Because it's 0 minus 1, the concentration, and then the Arrhenius reaction rate, which is the reaction constant, times E, okay, to the minus E over RT. Remember, E is the activation energy, okay? R is the universal gas constant. Okay, that's the rate of change of the concentration of the reactant, okay? But we really want to monitor the temperature, okay, inside. So how do we do this? Well, let's write down a statement of conservation of energy, right? So the variation of internal energy will be equal to the heat exchanged with the surroundings and the work exchanged with the surroundings, okay? Of course, this is a constant volume vessel, and so dV is equal to 0, okay? So we don't have this term here, okay? We also have the fact that du can be written as the constant volume heat specific heat at constant volume times dt. This will be equal to dq. Okay. So we can immediately construct an ordered differential equation, because if we, for example, let's multiply by the density, okay, CV, and divide by dt, okay, time differential, okay, we have rho dq by dt, okay. Let's look at a little bit the units. Always look at the units, okay? So we have here kilogram per cubic meter, okay? The CV will have kilojoules per kilogram per Kelvin, and then we have Kelvin per unit time, okay? So what we have here, okay, the mass and the kelvins go, okay, we have an energy per unit time, so we have essentially a power, watts per unit volume, okay? So the right-hand side here, rho dq by dt, well, we can actually write it exactly as we had anticipated, as the difference between a positive and a negative input, where all of these inputs are essentially measured in watts per cubic meter. Okay? So that's our equation regulating the temperature. Of course, now we have to somehow express the right-hand side. We have to express Q plus and Q minus. How do we express that? Well, for Q plus, okay, we can define a quantity QR, okay, which we measure in kilojoules per mole, okay, which measures essentially the heat of reaction, okay, very simply. The amount of energy released per unit mole of R, which is reacting. And so clearly Q plus, okay, can be expressed as this quantity QR and the rate of change of molar concentration of the reactant. Why? Well, because if this is in kilojoules per mole, this is a molar concentration per unit time, so it's mole per cubic meters per second. And so, again, this is measured in watts per cubic meter, a power per cubic meter, okay? And how do we express dC by dt? Well, we already have, okay? It's over here. And so it would be minus QR C K E to the minus E over RT. Okay? So we have an expression for Q plus. What about Q minus? Well, Q minus is the heat lost through the vessel walls. We keep the vessel walls at a constant temperature T0, okay? So we can use an expression which you may be familiar with, which is an expression for a convective heat flux, okay? So you have some kind of constant H. Let's multiply here by the area and by the volume, okay? And then a difference in temperature, okay? H, well, this quantity here, and in particular H, is essentially measuring the, it's a constant, it's a convective constant, okay? It's measuring essentially the fluid dynamic aspect of the boundary layers, okay, in the fluid boundary layers. And it will measure essentially the ratio of the convective heat flux with respect to the overall heat flux. So you may have seen this many times in heat exchangers, as well as in rocket cooling systems and things like that, okay? As you can see, so again, let us remind, so we have a vessel of volume V of area A kept at this temperature T0, okay? H is a constant which, because this has to be watts per meter cubed, okay, H has units of watts per meter squared per Kelvin, so that the Kelvin cancels out with the Kelvins here cancel out with the temperature, and then you have another per meter here, meter to the minus one, okay? So we have Q plus and Q minus. And as you can see, this is exponential and this is linear, okay, with temperature. So we have an overall system, as usual, a system of ordinary differential equation. For the temperature, it will be rho CV dt by dt equals Q plus dot minus Q dot minus, which is equal to, again, QR minus QR CK E to the minus E over RT, okay? Minus the Q plus, the Q minus part, which is HA over V T minus T0, okay? And what about C? Well, we also have to write down the equation for C, which is minus CK E to the minus E over RT, okay? And that's our system. Now, I could, for sure, what I could do is I could plug it in a numerical solver, okay? Use realistic values of density. The density will be constant, clearly, okay, because we're in a fixed volume, so the same mass and the same volume, okay, of the vessel, and monitor and integrated in time, okay, and monitor both the temperature as the concentration will go to zero, okay? But we can do a simpler thing for the time being, okay? Because looking at the form, okay, the rate of change, okay, of temperature is really the difference between two terms, which we know. We know the functional the functional form, okay, of these two terms, Q plus and Q minus. So what we can do is at least graph them, okay, represent them in a graph as a function of temperature and compare them, because if their difference clearly between these two graphs at a given temperature is positive, so if Q plus is bigger than Q minus, then the temperature will grow because dT by dt is bigger than zero. And obviously, if it's negative, the temperature will decrease. And if they're the same, essentially, there's going to be an equilibrium, right? So we have, let's have more space here. So let's have like a sort of a graphical interpretation of this. So on the x-axis, I'm going to put T. Now, T is the gas temperature. Now, inside the vessel, okay? And let's start this graph from T0. T0 is, again, T0 is the wall temperature, and T is the whatever temperature it is inside the vessel, okay? Well, again, we have two terms here, Q dot plus and Q dot minus, right? So these are what I want to draw. I want to draw on this graph. Now let's draw the easy thing. Q minus is a linear function, and so here, well, I'll draw two because clearly the slope of Q minus dot is decreasing as we decrease this function, this constant here. So if you decrease either the area, okay, or you increase the volume, for example, you will have a less kind of efficient cooling system, okay? And so the slope will go down. Now, what about Q plus? Q plus is clearly an exponential function, okay, of the temperature. I can roughly draw it like this, for example, okay? Indicated as Q dot plus, okay? If you draw it on a graph, well, if you start from t equals 0, then you have essentially 0 here. So e to the minus infinity. So you start from 0, and then so as t increases, and then it kind of goes like that. Okay, it will plateau to 1 as t goes to infinity. As t goes to infinity, because it will be e to the 0. Okay, so this is this is 1. And again, it represents the fraction, if you remember, of molecules having energy bigger or equal to the activation energy. Okay. In fact, if you remember E over RT, we could write it as the activation temperature. Okay. And the Arrhenius number, which is the activation temperature over the adiabatic temperature. So, for example, T max was something of the order between 4 and 60. So it's extremely high. So TA is really much bigger than your average temperature. Okay, so TA is somewhere over here. Okay, and T max will be maybe over here. Okay. So if you bracket between T0 and T max, you have essentially a function, okay, here. You have a function of this kind here, okay? So it's a qualitative, it's a qualitative picture, this one, okay? So let's go even further, okay. Now, first of all, you'll see that there are at least 2 points here where the two graphs intersect. So in these 2 points, Q plus is equal to Q minus. And as we said, those are equilibrium points. Why? Because it means that the temperature remains constant. Okay? But other than that, okay, let's see, let's start from the beginning, okay? And let's see what happens if I actually start my system at an initial temperature equal to the wall temperature. So we start from here, okay? So T, my gas temperature, okay, T is equal to T0, okay? As you can see here, if we look at Q plus and Q minus, well, Q minus is 0, but Q plus clearly is non-zero. So there is going to be a certain heat, chemical sort of heat added through the exothermic reaction. And so dT by dt, okay, will increase. So we're going to essentially move to the right, okay, here, until we reach this point here, right? Let's call this point F, for example. So the system has produced heat, but at the same time, as the system heats up, okay, it will lose more and more heat to the surrounding, okay? At some point, you will have that the heat production and the heat loss will balance out. So we've reached a stationary point. Now, what this point is, it's actually a stable point. Let's write it here. Well, think about it. You perturb this point here, a little bit to the left and a little bit to the right and a little bit to the left. Suppose that we perturb it a little bit to the right, so we increase the temperature, okay, above TF. As you can see, Q minus on the right will be a little bit larger than Q plus. So there is going to be an excess of heat loss, so the temperature will decrease and go back to TF. On the other hand, the opposite will happen if the temperature decreases a little bit. So a very stupid stability analysis will tell us that TF is constant, okay? Sorry, TF is an equilibrium point, okay? Now, I hope you understand that we're not really integrating any system here. We're actually doing what we call a steady state analysis of the system, okay? We're just comparing the source terms, nothing more, nothing less, okay? Um, Now, obviously, if you let it go, this is not going to stay here forever. It's not going to stay at TF forever. Why? Because as time goes on, what happens is that you decrease the concentration of the reactant, okay? And so the reaction rate will tend to decrease until essentially the temperature will go back and will revert back to the initial temperature T0. Okay? But in a steady state view of things, TF will remain constant. Okay. Now, what about the other point, the other equilibrium point? What happens if the temperature is brought all the way up here? So we don't start from T0, we start from this point here, for example. We bring the system artificially by heating it up to a point we call point G, okay? Well, something quite opposite happens because if you perturb the system now around G, well, suppose we decrease the temperature a little bit below TG, okay? Then you see that right away the cooling system takes over because Q minus is bigger than Q plus, and this poor system will cool down all the way down to TF. So this is for sure an unstable point, okay? On the other hand, if we increase the temperature, okay, above TG, then you see what happens. This is sort of a very, it's a unique kind of temperature, this one, because as we increase it, it's for the first time we have the fact that Q plus is actually bigger. So the heat generated within the vessel is actually bigger than whatever possibility you have of cooling the system. And so the system explodes. So from then on, the system explodes. And you can see that the mechanism now is a thermal mechanism. We haven't talked about any radicals or anything. Okay? So there is also this sort of thermal explosion mechanism. Okay? We call this TG, okay, an ignition temperature. Okay? As you can see, the ignition temperature is well above the wall temperature T0, okay? Now, you see that we can manipulate the cooling system here by, you see, I'm adding an arrow here to say that if you suppose that H is constant, okay, we can manipulate the system by, for example, decreasing AV, okay? So if we decrease, so the arrow down, pointing downwards means as we decrease AV, we have these lines that are of less and less slope, of a smaller and smaller slope, okay? In fact, we can decrease it to a point where, and of course I will never be able to do this, the two curves are Ooh, okay. Our tangent. You agree? So we're not changing anything chemically, so we're not changing the curve there, we're not changing anything, but we're changing the area to volume ratio. And in fact, we're decreasing the area to volume ratio so that we essentially move from this curve to this curve, and so from the higher curve here to the smaller and to the lower curve here. Okay. What's so special about the tangent curve? Well, no stable equilibrium point exists. In fact, there is this tangent point. Okay? But if we decrease it even more, okay, like this, well, the cooling system is so inefficient that at any temperature, including the initial temperature, okay, you have explosion. Okay. So this is phenomenon is we can call it self-ignition. So for this particular curve, you have self-ignition in the sense that for all the possible choices of temperature, you always have a thermal explosion. Okay. um, so you're starting to begin to start to understand how this thing is working, right? There's this competition which is not at all obvious between the heat loss and the heat addition. In fact, it's not even obvious because this um, system also depends on other parameters. For example, how does Q plus depend on pressure, for example? Well, remember that dC by dt is minus CK e to the minus E over RT, right? So this is essentially for the reaction R going to the products. And it's an irreversible reaction, okay? In fact, it is so generic, let's make it even a little bit more generic. Let's add a reaction order here, N, okay? And if there is an N here, there's also an exponent here. So if the generic reaction is of order N, then this goes to the exponent of C here in this expression, right? Now remember that, I'll write it over here, the molar concentration is the partial pressure divided by RT, so it's essentially the mole fraction times the total pressure times divided by RT. So we can write here something like minus xi to the n, p to the n, okay, RT again to the n, k e to the minus e over RT, okay? So again, this is a long story short to tell us that if we indeed represent, okay, we're almost done, Q plus as we did before. So the heat of reaction times dC by dt, you see that through this term here, we can say that Q plus, okay, also depends on pressure, okay, very roughly said, okay, it can be considered to be proportional to the pressure to the power of n, okay? And so what does that mean? Well, it means that if we have the same graph as before, Okay, this is Q minus, and we have our Q plus. If we increase the pressure, okay, it could even be that we move this this curve over here, and so by increasing the pressure, this favors self-ignition, because as you can see, we go from a point where you only have ignition at this point here to the second curve, okay, where you have ignition at all temperatures. So the pressure will play a role, okay? And well, I'll continue next time with all of this. Okay, and soon we're also, let me just say this, we're also going to have a lesson with Pasquale Lapena as my colleague, collaborator, about the most recent techniques of computational techniques on turbulent combustion. So what we're actually doing in terms of research. So what we're doing here is a very basic approach to combustion, but then I'd like you also to see if you stay on, for example, for a thesis or something like that, this is the stuff that you will be handling. So computational combustion coupled with fluid dynamics. Okay, this is what you will be doing. So sometime in the next, maybe next week. Okay, and I suggest that you follow it because it's very interesting. Okay. Okay, stop recording.